The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start with review and preview. I put a P up there because we're really looking into the Fourier part that just started this morning. But maybe, and there'll be some homework from these early sections about the Fourier stuff. So maybe we should just do a few of those problems or discuss here today, just in advance. Can I say one thing about MATLAB and the MATLAB homework first, and maybe open a conversation about it? So there are really two different problems that I'm personally quite interested in. One is two model, I'll say model problems, because they're for regular polygons in a circle, and I'll draw an octagon again, so m sides, and I'm interested in as m goes to infinity. And I'm interested in two different problems. So one of them is our MATLAB problem minus is the Laplace's equation. What was it, 4? With u equals 0 on the circle. Okay, so that's our problem, totally open for discussion. How many have started on the... Oh, good. Okay, well then you all know more about it than I, and that's great. I'd be happy to learn. So if I said everything there, yeah, we've got Poisson's equation inside. We've got u equals 0 on the circle, so the problem's well defined, and the solution should be 1 minus x squared minus y squared. No, yeah, 1 minus x squared minus y squared. Right. Okay, so that's the correct solution. Maybe I could also tell you about the second problem that I'm interested in, because it hasn't come up in class, but it's very important too. It would be the eigenvalue problem. So this is problem number 1, the steady state problem when you've got a source and you want to find out the temperature distribution. Problem number 2 would be the eigenvalue problem, minus uxx minus uyy. I take those minuses so that the eigenvalue will be positive. So that's what the eigenvalue problem might look like. And again, let me say with u equals 0 on the boundary, on the circle. Okay. So this is, person would say this is Laplace's eigenvalue problem, because we have Laplace's equation. We've got eigenvalue, so it's, as always, it's not linear, because we have two unknowns. Lambda's multiplying u. And we have boundary conditions. And this would describe normal modes, for example, of a circular drum. If I had a drum or a polygon drum, so if maybe I connect the, to actually build the drum, I might fold in the sides there and have a polygon. And again, I hope that the eigenvalues of the polygon, this equation in the polygon, which are not known, by the way. To the best of my knowledge, we know it only for m equals 3, which would be an equilateral triangle, and m equals 4, which would be a square. And those eigenvalues, because of Fourier or something, are humanly doable. But I think 5 on up is, I may be wrong about 6, but I don't, I'm not sure about m equals 6. A hexagon sometimes gives you enough help, but beyond that, you're on your own with finite elements to help you. So there's a whole sequence of eigenfunctions, u, and eigenvalues lambda, just the way there were in one dimension. And on the circle, they involve Bessel. That's where Bessel, you know, he showed up. He figured out the functions, and they're not especially nice functions. You know, but they're studied for centuries. Bessel functions come into that. But here I have the same question. I mean, let me just say, for me, this could be a Europe project if anybody was an undergraduate, or it could be a project over January or something. I'd like to know something about what happens as m goes to infinity as the polygon approaches the circle. So I'm hoping maybe on some of the homeworks that come in, you'll if it's not too difficult, and maybe it's not, to let m go up a bit. There is one thing, that the code we're working with is linear elements, right? We're using linear finite elements, so we're not getting high accuracy. So I would really like to move up to quadratic elements, but at least those, you remember quadratic elements would be ones where, well, first I have let me draw the one that we've drawn in class before. We only have to look at one triangle, and then we cut it up into triangular elements by taking some pieces here, taking the points above, which I hope are now correct on the website, connecting those edges, and then connecting these. Is that right? Is that our mesh? Okay, and then so that mesh is controlled by n, 1 to n points. So also n is going to have to get large too to give me accuracy. And another way toward more accuracy is, instead of linear elements, second degree. So do you remember I wrote those down? Say, let me take that little triangle out here as a bigger triangle. It would look something like that, I guess. The second degree elements have those 6 mesh points. You remember I drew those, but we didn't really have time to get further with them. The functions, the trial functions phi, which are 1 at a typical mesh point and 0 at all the others, they're computable because we just have, but we're up to second degree, so it's a little, second degree things. Then the first derivatives, which come into the integrations, are linear and not constant. So a little bit harder. But finite elements, linear or quadratic or higher, could be used for this problem, as we know, and for this problem. What I wanted to add that I've not mentioned in class, and I think we may just not get a chance to do it, is what does the finite element method look like for an eigenvalue problem? Because eigenvalues are highly important. That's the different way to understand. There's the matrix K and its entries, but then there are the eigenvalues. And you might think, what do you think is the discrete eigenvalue problem copying this one? Here's my point. Your first guess would be, well, this is like K, right? This is like KU, right? Our K2DU, I should call it, maybe. Well, sorry, I'll call it K because K2D I have specifically reserved for the Laplace eigenvalue, Laplace stiffness matrix on a square mesh with triangles, the K2D. That was one specific matrix for one specific mesh, and here we have a different mesh. So I should just call it K. Okay, I think if anybody was going to make a guess, they would say, okay, Ku equal lambda u. Maybe I use capital lambda because I'm using capital U. Is this the finite element method eigenvalue problem? And if you answered yes, I would have to say, well, that's a reasonable answer. But it's wrong. The eigenvalue problem, when I take the differential equation for the Laplace's equation, with lambda u on the right side, and I go to do finite elements, it produces K out of this stuff, out of the weak form, all that stuff, but it produces another matrix on the right-hand side from the constant term, and we have not really mentioned it. It's the mass matrix. So this, instead of just the identity here, there's a mass matrix. So that is the problem that you could do. I could have made a MATLAB project. I guess I bet I do it next fall, right? You guys did the first one, this one, or you are doing it now, and I'm going to pause in a minute for questions about it or discussion of it. But this one brings in something called the mass matrix. So let me just say what those are. Yeah. Well, if I write down the entries in the mass matrix, you'll sort of get an idea of why they are. So what are the entries in the stiffness matrix? Kij, you remember, is the integral of the phi I dx, d phi j dx, plus d phi I dy, d phi j dy, dx dy. And that's what you're computing, and that's what that code is computing. And when phi is linear, then slopes are constant. So all you have to do, and what that code in the book is doing, is figuring out what are the slopes. This thing's a constant, so we just need to know the area of the integration. Where are we integrating the area triangle by triangle? Fine. That's what we're doing. That's what that code is just set up to do. Now I have to tell you what is Mij, the mass matrix. I just think you don't want to have. We haven't done too badly with finite elements in here. You know, we did it in 1D where we got it kind of straight, and now we're seeing what it looks like in 2D, but I had not really mentioned the mass matrix. So here it comes. The mass matrix will be the integral of phi I times phi j dx dy. It's the zero order, no derivatives, just plain zero order, as you'd expect from the fact that the term in the continuous part is zero order. So it's this mass matrix that comes in. And maybe we could just look to see which entries will be zero and which will not. How sparse is it? What does the mass matrix look like? Can we just, let me do 1D first. So there's a phi, right? There's another one. There's another one. So what do you think about the mass matrix? One phi multiplied by another phi and integrated. Is it diagonal? No, because phi, each phi overlaps its two neighbors. So tell me what kind of a matrix M is going to be in 1D. Tridiagonal. Tridiagonal. It'll be tridiagonal. Now, so was K. So K and M actually have non-zeros in the same places, the same sparsity pattern. But, of course, not the same numbers in there. K had like -1s and 2s or 4s and -1s. This matrix, well, actually, what can you tell me about this tridiagonal matrix? When I integrate that against this, well, again, I would do it element by element because this against this, they only overlap here, right? I'll just draw the one place that they overlap. And what's the point? They're both positive. So the mass matrix is, its rows don't add to 0. Its rows tend to add to 1. But it's not diagonal. That's the difference. Okay, so that's, I just felt I couldn't feel, you know, I wouldn't have done a decent job in describing finite elements if I didn't describe this, didn't mention this mass matrix. And maybe I better say where it comes from. Yeah, well, because eigenvalue problem, it may come number 2, but that's pretty high up the list. So let me tell you where does this mass matrix come from? Well, first let me tell you about eigenvalues of a matrix eigenvalues. Yeah. So the answer was, is this the finite element eigenvalue problem? Only if there's an M there. And now I want to, okay, first of all, what MATLAB command solves that problem? Let's just be a little practical for a moment. What MATLAB command gives me the matrix of eigenvectors, the matrix of eigenvalues would come from eig of what? If I want, this is, I'd call this the generalized eigenvalue problem. Generalized because it's got somebody over here. And it's just K apostrophe M. Or, of course, you get the same answer. Well, you get the same eigenvalues. Well, I guess the same eigenvectors, yeah. If you, or eig of M inverse K, of course. If you want to do it with just one matrix, then bring M inverse over here. But M inverse, the inverse of this tridiagonal matrix, is full. No zeros in the inverse. So everybody would much prefer this tridiagonal one. So that's how MATLAB would do it. And what I want to know is, back in this problem, how close do the finite element guys come to on polygons, come to the correct solution on circles? I'm hoping that for problem 1, you can maybe keep M and N equal, or maybe N, maybe 4 times M or something, and let them grow and see, well, for example, at the center of the circle, or how quickly do you approach the correct answer, 1 at the center of the circle? I think it's going to be a good problem. Let me open to, so I started out just talking there. What about the MATLAB problem? You've made a start on it. Is it going? Have you got a graph maybe of the, or what's reasonable to graph to give Peter to look at? Who's done something on that MATLAB problem? Yeah, go ahead. Tell me tell us all what to do.
I made the triangle bisecting and
okay.
charted U over it.
Right. And did you?
Looks symmetric.
Okay.
I didn't find an error that changes
with m more. Yeah, I see. So was n, if you just fixed m like 8 and let n get,
I found the error didn't change.
it didn't change significantly, yeah. It wouldn't, of course, converge to the right answer. It'll converge, if it does, to some kind of an answer to the, for the polygon. Right, that's right. So I, you know, as I wrote the problem, I didn't know whether I dared say, let m get increased too, but of course that's the real question.
I tried that too, and then I found
And what happened then?
the error did shrink.
The error shrank. Okay, and now maybe it's possible to see how fast or something. That's always.
I was thinking about making a 2D plot of m versus n and graphing the average
Ah.
error over that.
Okay, at the center. Okay, and can I just, then I'll have hope for more comments. Let me say one more thing. My theory is that the error at the center is quite a bit smaller than the error closer to the boundary. I would be interested in an error. Is it fairly even? Whew, my theory is wrong. It wouldn't be the first time. But, and maybe it's because it's linear. Yeah, my theory is more for better elements like these. I don't know. Okay, but I'd be interested to know. Yeah, this, why do I think, why do I have this theory, which you guys are going to prove wrong anyway, but still, after you've proved it wrong, you won't listen to me if I tell it to you. So now I'll tell it. My theory is that the error around the boundary is sort of, you know, there's no error at these vertices, and then there's sort of going to be an error because the real answer is not 0 along here. It's sort of near 0, but not quite, you know, there's an error. So there's errors around here from getting the boundary wrong, squaring it off. But my theory is that errors, the boundary stuff, drops off quickly as you go inside. That's why I think, you know, from those, you remember those, well, we'll see them again either today or Friday, those r to the nth cos nx type things, that cos n theta. Yeah, you remember those are the typical solutions to Laplace's equation. And then, so that and it has some coefficient, of course, an. And I look at that, that might be a piece of error. And it's way bigger when r is 1 and way smaller when r is 0. So anyway, that's sort of my theory, that if you have, like physically, you have like a circular plate, and you're maintaining the boundary temperature at some sort of oscillation, like near 1 but up and down from 1. Then I think further inside, it doesn't know. It hardly knows about that oscillation. This is my theory, that inside toward the center of the circle, it only sees kind of an average boundary temperature and not your little ups and downs. So when m is big, I expect that part of the error, the up and down part, to be not so significant in the center. Anyway, now that's my theory. Yeah.
Are you interested in absolute error or percent error?
Ah, good question. Whew. Okay, so if we only looked at the center, would it all be the same? Would it? I mean, if we're only looking at that one point where it should be 1 at the center, but along the thing, I don't know. If you look at both and see a significant difference in the behavior, I'd be interested. Yeah, yeah. You know, all these problems are things that there's no single solution to. Yeah.
What I found when I did it was that the error between the u, that 1 minus r squared, and
The error between 1 minus r squared.
was mostly dependent on
Ah,
was entirely dependent on n and almost not at all affected by n.
oh, right. We've got slope error, too.
So yeah, as n
That's a
increases,
very
it
significant one.
exactly matches the minus 2n.
I see. Right,
For lower n's.
right. So there's slope errors in there. And everybody knows then, everybody in working the problem, I mentioned that the boundary conditions on this piece of pi were 0 along here, and normal derivative, somehow it got printed du dh, but that was an accident. It should have been du dn. dn is 0. So Neumann conditions on the thing, and then I was a little scared about that point, but I think phooey on it. It's just don't worry about it. But what I was going to say, what do you do to take into account this du dn equals 0, this slope condition on these long boundaries? What should you do in finite elements to take account for that? And the answer is, in one nice word, nothing. Right, nothing. Your finite element method should not, you don't impose any condition along these boundaries. You just use the code as it is with zeros on this boundary, and it should work. Yeah, it should work. Any comments on other people? What did you get reasonable results, or tell me something, because you guys looked at those graphs and I have not. Any feedback yet on those? I'm happy to get email too about feedback. I mean, so all the email, first of all, that corrected the typos in the original coordinate positions, and now that pointed out I better look at M, is very, very welcome. Yeah, yeah. It doesn't mean that everybody has to do this. You know, if you've completed that MATLAB assignment, you never want to see it again, and you kept M equal 8, it's okay. But if you're interested to see what happens if M goes to 16 or 32, I'm interested also. Right, yeah, yeah. Okay, so anyway, that's the problem we're really thinking about, and that's the problem that is equally important, but it seemed reasonable just to do one of the two, right? And we were set up to do, we have the code for the stiffness matrix. We would need a new code to do these integrals. Because this will be linear times linear, right? It'll be this, I'll have to compute that one times this one, and I would need new formulas that are not in the, I need formulas for, this will be linear times linear, so I'll be integrating x squared type stuff, and xy's, because I'm in 2D, and y squareds, so it would take a little more code, but not much. Yeah, yeah, I think the mass, oh, here's a question for you. Here's a question for you. Suppose I have my trial functions, phi of x. What do they add up to? Let me again draw a mesh. So I've got a mesh. These are, you know, I'm sorry, I want to put in some more triangles here. Lots of triangles, whatever. Let me get some more vertices too. I'm getting in trouble. Okay, whatever. So phi is the piecewise linear guy that is 1 at node I. So I've got all these different nodes. Here's, oh, there, I need a node there. So I've got 1, 2, 3. There's a node. There's more nodes. If I add them all up, this is just like an insight question. I've got all these, well, you could add up these hats in 1D, What's the sum of the hats in one dimension? 1. Good, good, good. The sum is 1. It's a nice fact that these guys add up to 1. And now, why is it still true here in 2D that these little pyramids will add to 1? Yeah, that's an insight question. It's worth thinking about. Why do those pyramids add to 1? Let me leave that question for. I'm thinking of it. We haven't imposed any boundary conditions yet. We've got them all, and I claim that if we add up all the pyramids, including the boundary, chopped off pyramids from the boundary, that we'll get 1 throughout the whole. Now it'll be phi of x and y, because now I'm moving to 2D with pyramids, and I think we'll still have 1. Let me give you a minute to think about that one. And then we could turn to Fourier questions if you would like. We could do some problem from the text. Any thoughts about this guy? Why should all those individual pyramids add up to a flat roof? Why did it work here? Well, it worked because you could see it, right, somehow. Does it still work if the nodes are not equally spaced? So we've got a hat function for that guy, and a hat function for this guy, and a hat function for this guy, and these guys are in there too. We haven't imposed anything. So those 1, 2, 3, 4, 5 functions, 5 phis, they add up to 1. And why? Well, you're going to say it's obvious, but that's what professors are allowed to say. Things are obvious. You have to actually say why, which is not as easy. So why do they add to 1? Let me look inside one element. Why do the sum of these two guys add to a flat top inside that interval? Yeah.
On either endpoints that it's at 1.
At the endpoints, you've got it, because at the end, what's happening at the endpoints? This guy, one of the guys, the right guy is 1, and all other guys are 0, right? And this guy is also at 1, because its right guy has height 1 and all others 0. So at the nodes, we are at 1 because of one person, really, one element. Yeah, and then?
As you step, if you look at the one you labeled as 1,
right.
to the right, it's
Yeah.
going to decrease by a little amount, and the other one's going to increase by the same amount.
But the sum of them is? Why is the sum of them always 1? Why is slope 0? Yeah. Yeah. Yeah, the slopes cancel, right? Or we know that in between it will be a linear function. That would be one way to look at it. If I add up a linear function and a linear function, the sum is a linear function. So I'm getting a linear function which is 1 at those points. So what is that function? 1, right. That's the straight line. So that idea will work here too. If look inside some little triangle here. Okay, that's got 1, 2, 3 corners. Okay, and if I look at this sum, what is it at this corner? If I look at that sum at this corner, one guy is 1, the one for that pyramid, and all others are 0. So the sum is 1 there, the sum is 1 there, the sum is 1 there, so that on this blowing up this little triangle, this is at height 1, this is at height 1, this is at height 1. So what's the roof? Flat. Yeah, it's just a nice way to see the nice property of these phees, that there's a phi for every node, and they add to 1. Yeah, so that's good. Okay, I've said, well, I was going to say one more thing, and I am, about this eigenvalue problem, just because I'll never have a chance again. So this is the moment to say something about the eigenvalues. Lambda, eigenvalue. I'm answering the question, where does k come from? Where does m come from? Well, the eigenvalue is, boy, we've really got dramatic music here. Is that the Great Gates of Kiev? I think might be. Mussorgsky. If you like drums and big noise, it's not music actually, but you get a lot of noise out of it. Well, of course, he knows more than we do, but still, anyway. Okay, so the eigenvalues, in the matrix case, for k, x equal lambda mx, the eigenvalue problem, lambda, the lowest eigenvalue, lambda lowest, it has a nice property. It's the minimum of our energy over our other energy. I just think, well, this is something you should see. That this is a quotient here. It's got a name called the Rayleigh quotient, and it would appear in the book. So really, I guess what I'm doing is calling your attention to something that's in the book. That this ratio of x transpose kx to x transpose mx, if I look over all vectors x, the lowest one is the eigenvector. The best x is the eigenvector, and the ratio is the eigenvalue. Right, yeah, this is like my point, that I wanted to mention the Rayleigh quotient. Here it is in the matrix case, and there would be similar Rayleigh quotient in the continuous case. I'll just leave it at that. That in describing eigenvalues, we can talk about kx equal lambda mx like this, or we can get energy into it. And you remember, the whole point about finite elements is, look at the energy. Look at the quadratics. Multiply things by things. That's something that came from the weak form. It didn't come from the strong form. In the differential equation here, we just have single terms. We got to these things through that process of multiplying by u's and integrating. That's what gave us these products, and it works also in the matrix case. Okay, that was a lot of speech making about topics that we simply didn't have time for in class. I'm ready for any question, or I'm ready to maybe do a Fourier example. Would you like that? Because this is where we really are. Yeah, I'll even take one that'll be on the homework, just so you'll have a start. Okay. Let me take a square pulse. Yeah, this is a good one, I think. Yeah, this is a good one. In section 4.1, there's a question for the Fourier series of a square pulse. Okay, so what does the square pulse look like? Here's minus pi to pi. Here's 0. The square pulse goes along here, up, square pulse, and down. Actually, maybe the one in the, let me go to L over 2. I'll call it H. Let me find the the Fourier series for this function. It goes along at 0. it jumps up to 1 over an interval of length 2h, going from minus h to h, and then back down to 0, and then repeats. So, boop, 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 square pulse. So that's my function. Is that function odd or even or neither one? It's even, so I can call that c of x and figure that I'm going to use cosines for that one, right? Okay, so tell me a formula for the coefficients. What's the integral that I have to do? So my c of x is going to be some a naught. We have to think what's a naught, and then a1 cos x, a2 cos, and so on, ak cos kx. Okay. What's the formula for AK? Before I plug in that function, I would like to get the formula. So I'm looking for the formula. It's a formula to remember. So it's really, I'm not wasting your time, because you're going to see it on the board and it'll just take a mental photograph of it. What do you think it's going to be? How am I going to get it? I'll multiply both sides of the equation by cos kx, right? And I'll integrate. So, and then when I integrate, the cosines are orthogonal, just like the sines this morning. All those terms will go, except for this term. When I multiply this by cos kx, I'll have cos kx squared. Here I'll have a cos kx. And here I'll have a whole lot of cos kx's, but when I integrate, all this stuff is going to disappear. The only one, and this will all disappear. This is it. So AK is going to be the integral of my function times cos kx dx divided by what? Divided by the integral of cos kx squared. Because I haven't normalized things. So I don't know that that's 1, and in fact, it isn't 1. So I have to remember, put that number in. Okay, so that's the formula. And that number turns out to be pi, again. If I'm integrating from minus pi to pi, then the average value of the cosine squared is 1/2. It's sort of as much above 1/2 as it is below 1/2. And so the average is 1/2, the interval is 2 pi, so pi. Okay, that's the formula. Please just take a mental photograph. Catch that one. All right, now I've got my particular c of x, my square wave, square pulse. Very, very important Fourier series here. Yeah. Famous one. Okay, so what do I have? From minus pi to pi, well, so what's my integral? Well, my integral really doesn't go from minus pi to pi because my function is mostly 0. Where does my integral go? Negative h to h, right? And in that region, what is c of x? 1. So now I'm just, you see, it's going to be nice. From negative h to h, where this is 1, I just have to integrate cos kx. So what do I get? Sine kx over k and the pi. So you see again that k is showing up in the denominator, and that's going to give me the typical decay rate of 1 over k for functions with steps, for step functions. And now I have to evaluate this between minus pi and pi. And no, h, better be h. Between minus h and h. So what do I get for that? I get sine kh, right, at the top. And what do I get at minus? So now I want to subtract. What is the sign of minus kh? It's negative, right? So as I expect with an even function like cosine, am I just getting twice? I could take it from 0 to h, and it would give me one of them, and the other one, yeah, I think so, and divide by k pi. So those are the Fourier coefficients, except for A0. A0 has a slightly different formula, because for A0, well, yeah, why is A0 different? How do you come up with A0? And what's its meaning? A0 has a nice meaning. So this is, yeah, this is worth having come this afternoon for. A0 will be what? Well, I could get it the same way. What will I multiply both sides by? If I want to pick off A0? Just 1. It's not a cosine, it's the cosine of 0x, it's the 1. And then I integrate, I'm just going to get the integral from minus pi to pi of c of x times 1 divided by the integral from minus pi, that's to pi of 1 times 1. Right? dx, sorry, that should be a little higher, dx. Right? Same method. Multiplied both sides by 1, which was the very first of my orthogonal functions. Integrated, all the other integrals went away, right? The integral of cosine over a whole interval, it's periodic. You get the same at the two ends, so its difference is 0. So we just, the only term left was the constant. And now what is the integral? What's the denominator now? That was the little slight twist. 2 pi. Denominator is 2 pi. Yeah. That's why it's not, yeah, it's slightly irregular. I have to divide by 2 pi. And now, what word would you use to describe? If I have a function and I integrate it and I divide by the length, what am I getting? There's an English word that would describe what this is. Average. Thank you. Average. This is the average. And it has to be. This constant term is always the average. And what will it be for this? So this was AK. And what is it? What is A naught then? So what is, you can now tell me, so everybody's remembering this formula. You integrate the function and divide by the 2 pi. Now we've got a particular function, so what is the integral of that function? So what does this equal for this particular c of x? What's the area under that function c of x? 2h, right? So 2h over 2 pi, cancel the 2's. So there's the constant term. A naught is h over pi, and the cosine terms are, yeah, actually we're going to get something nice. A really nice way to complete this will be if I put this together, put this series together. So now I'm saying that this square pulse is the constant term, h over pi, plus the next term, a1. Well, let's see, all these terms have 2 over pi's. Why is that? Yeah, I'm a little surprised that's h over, yeah, no, I guess that's right. 2 over pi. Yeah, right. So I've got sine h, I think, and now I'm just copying this. 2 over pi sine h, sine h, is that what I want? Over 1. That's the coefficient of cosine x. Right? That was A1 was the coefficient of cosine 1x. And then A2 is the coefficient of cosine 2x. So that'll be sine 2h. K is 2, so I have a 2 down here, cosine 2x, and so on. Yeah, I think that's the Fourier series. That would be the Fourier series for the square pulse. Yeah, that would be the Fourier series for the square pulse. Could I test any interesting cases? Suppose h is all the way out to pi. Yeah, suppose I take that case. Let h go all the way out to pi. Then what's my function? If h equals pi, then what have I got? What have I got a graph of? Of just 1. It's just a 1. If h is pi, what happens? That becomes a 1. And what about these other things? What is this thing when h is pi? 0. All the other terms go away. It's just a sign of 2 pi that would go away. Yeah, so if h is pi, if I go out to the place where I don't have any don't have any jumps at all, because it's now all the way out there, then these terms all disappear and I just have this. And I would like to ask you, and it's got to come up on Friday too, what happens if h goes to 0? Well, let me just take h going to 0. What happens to this whole thing? What happens to my function as h goes to 0? It goes to 0, right? Squeezed it to nothing. And if h is 0, then sine h is 0. Nothing. I get 0 equals 0. That's not interesting enough to mention on Friday. But there is one case that is important. Suppose I make the height. Yeah, make a guess. Suppose I make the height. I make the height higher as I make the base smaller. I'm going to keep the area as 1. So I'm going to, if this has a base of 2h, I'm going to have a height of 1 over 2h. So if I keep the area at 1, so the height now is 1 over 2h. So now my square pulse, I've divided it by 2h. I have a 1 over 2h multiplying everything. And now if I let h go to 0, something more interesting will happen. And just tell me first, what do you expect to happen? Delta, right, delta. So I'll get, what I'll see show up will be the Fourier series for the delta function when I divide by 2h. So I have sine h's over h's, and of course, what's the great fact about sine h over h? As h goes to 0, it goes to, everybody know what that's the big deal. Yeah, 1. Sine h is the same size as h for very small h and approaches 1. Yeah, so we'll see the delta function Friday. Okay, so you got a sort of mini lecture instead of a real chance to ask about homework. Next Wednesday should be different because there will be a Fourier series homework, and I'll be ready to answer questions about it. Okay, thanks.